you did it. This is the last lecture of new material for the semester, so give yourself a pat on the back. Let's go ahead and we're going to look a very, very small amount into quantum physics today. So we're going to be looking at the Bohr model. We are skipping a lot of points up until getting to this point scientifically. We're not going to be looking into the full detail of what happens in the Bohr model, but I just kind of want to show you guys where you are going to be going on your physics journey, assuming you have to go to Physics 231. Last time we focused on resistor circuits, so we looked at Kirchhoff's laws. We had the loop law, which is a conservation of energy. That says the change in potential around a closed loop is going to be equal to 0. Again, we didn't explicitly talk about potential, but it is related to potential energy. We also had the junction law, which is a conservation of charge. It says all the charge coming into a junction of wires has to be equal to all of the current going out of a junction of wires. And we saw that you could have resistors set up in a series, so one directly after the other. And to find the equivalent resistance, so this is replacing all of those resistors with a single resistor, you just add those values together. If you have them in parallel, so this is where they're going to start and end at the same junction, but they're going to be next to each other like the L's in parallel. To find the equivalent resistance, you're going to take the inverse of the sum of 1 over all of the resistor values. So we're not going to really be using this, and by we're not really, I mean, the only thing we're going to be using from the past couple of weeks and today is the fact that an atom exists. So in this first video, we're going to go over Bohr's model of atomic quantization. In the second video, we're going to look at the Bohr hydrogen atom, and in the third video, we are just going to be doing an example. So let's quickly talk about the atom again. I just want to refresh kind of what we are going to be looking at. So an atom is made of a nucleus, which has protons and neutrons inside of it, and electrons. So these are some kind of common ways in which an atom is represented. So here we have our nucleus portion. It's N for neutrons, P for protons, and the electrons are these little negative spheres on the outside. And depending on what's happening in the nucleus, right, we can have different arrangements. We can have different numbers of neutrons, protons, and electrons. Now, this isn't by any way the accurate description for what this ends up looking like. Just a nice visualization of what's going on. So, for example, the nucleus is much, much larger than an electron. A single proton is about, I think it's 1,000 times and a little bit heavier than an electron. So this is by no means to scale. And we've talked about how electrons leave the atom to form a current, or in cases to form bonds or other things like that. So typically, when you look at atoms in terms of quantum physics, you're going to be looking at stationary nuclei and moving electrons. This is sometimes referred to as the muffin tin approximation, which basically says that if you have a, if you ever have had a muffin tin, right, you have some spots. So these spots would be the atoms, and then the place where the muffin doesn't go, that can be where your electrons go, pretending that doesn't go into any of the tins. So, there are a lot of approximations that end up being used mathematically, but, this isn't going to be really what we're getting into. We're going to be looking at a single atom today. We're not going to be looking at something that gets more into the structural behaviors of an individual object. So again, this is a visual model. It's not very accurate. This is actually a couple of atomic models old. but it just gets the idea across. So if you were talking about building up your valence electrons, this model's okay to show that. But again, it's by no means the most accurate. So we need to talk about absorption, because this is going to be what kicks off the idea of the Bohr model. So back when they were still discovering the different aspects of an atom, so originally the idea of an atom was that it was just this little solid sphere. And then it was found out that they had positive and negative charges, but they thought they were all clumped together. And then we kind of built up to this point where we said, oh no, there are, there's this nucleus, it's positive, electrons moving around the outside are negative. And so when they're still trying to figure out kind of how do we describe this new behavior, they had some atoms as a gas, and they put them into a couple different contraptions and shot some light at them. Now this light had specific wavelengths, and they found out that not every wavelength could be absorbed by this gas. So here we have the absorption spectrum of sodium. So here is the visible spectrum. We have red on the right, and we have our purpley color on the left. These black bars correspond to the wavelengths that sodium can absorb. Now below, I guess this purplish stuff is supposed to be ultraviolet, but anyway, right? So this is what is absorbed. Sodium, for this particular wavelength, whatever it happens to be, it's a little bit under 600. Sodium will absorb that wavelength. Sodium will absorb this wavelength here, which is probably around 325. These have exact numbers. They have very specific wavelengths associated with them. And below we have the emission spectrum. So the same gas was then done in a different experiment to see what light it would emit. What light is that gas going to put out? Well, it turns out that every wavelength absorbed is also emitted. So if we, draw a straight line down, this yellow light in the emission spectrum comes from the absorption spectrum. There's one here. Every single one of these drops down. However, if we look at this chunk in the blue to green area, even this one yellow one, this orange one here, couple in ultraviolet, right? These colors are not absorbed by sodium, but they are emitted by sodium. So a sodium gas can output all of these different wavelengths. Again, it is a specific wavelength. It has a value. It's not a range. It is one wavelength. Whatever numerical value that happens to be based on this spectrum. And the examples we're going to do, we are going to look at how you can calculate these wavelengths. So for the original models, when they were doing these experiments, they couldn't explain this. There was no way for them to go, oh yeah, based on how we have the electrons organized, this makes complete sense. So we needed to move on to a new type of model that accurately explained how only certain wavelengths could be absorbed and emitted. And so in order to do this, there was a lot of different stuff that needed to happen. In particular, we needed to start looking at the energy associated with these wavelengths. So if you go through and you combine a couple of equations, you find that the wavelength is equal to hc delta E. where h is something that is referred to as Planck's constant. C here is the speed of light. And delta E is some change in energy. So with this change in energy, right, Planck's constant is a constant, the speed of light is constant, and the wavelength is something that can be measured. So what they were doing to figure out what's, a way to explain what's happening here, they were focusing on the change in energy part. So with this change in energy, we have to think about, well, what's changing energy? Is it something inside of the nucleus? Is it the nucleus itself, or is it the electrons? And again, we have to remember that the nucleus and stuff inside of the nucleus is way bigger than an electron. So something is happening where the electrons are changing energy associated with a particular wavelength. And it's this change in energy aspect here that the Bohr's model does really well. Let's put an asterisk there, in a very limited set of situations. So let's talk about Bohr's model of atomic quantization. So this happened in 1913, so we haven't really understood the atom that long. Because even in 1913, our understanding of the atom, Bohr's model is fantastic. It helps us build up a lot of our understanding for what we end up using now. It was a fantastic starting point. It's a little outdated. It's really good for learning quantum mechanics, but it doesn't explain a lot of detail. So, you're still going to learn about it. However, understanding that Bohr's model is a model old. There's a different model, the Schrödinger model, that is more accurate, but it comes at a cost of being much harder to do computation. So you typically need computational methods in order to go through and solve it. So what Bohr's model did is it took the, at the time, most modern model, the Rutherford model, and said, well, there's quantization. Electrons could only have specific values. Now, when we had energy before in this class, we could have any value we wanted. Right? I can take an object and I can hold it at any height above the ground I so please. I can get on a ladder to put it higher, I can dig a hole to get it lower. And I can change it by a centimeter, therefore changing the energy by a fraction of an amount. Bohr says that's not true for electrons. They only can have very specific energy values. And so because we can only have specific energy values, what's happening is when light is hitting our electrons, it's changing the energy value associated with the energy of that particular wavelength. So what's happening is that light is coming in. Let's say we have our atom and we have a little electron chilling in orbit. What's happening is a wavelength is coming in, it's hitting our electron, and sometimes this color is going to be absorbed, and in other cases, it's just going to pass right on through. So what Bohr is saying is that because only certain energy levels are allowed, only certain wavelengths can be absorbed. And because only certain wavelengths can be absorbed, it makes sense then that only certain wavelengths can be emitted. Now, why more can be emitted, we'll have to get to in a little bit. But only certain energy values exist for an electron, and that means it can only absorb certain wavelengths. So let's kind of look at a nice little summary version of the atomic quantization that Bohr did. So here we have a single element. We have our nucleus and we have electrons orbiting around. These circles here are just representations of the different orbits that the electron can be in. So here on the left side we have what is referred to as a stationary state, and on the right we have another stationary state. So a stationary state does not mean the electrons are physically stationary. They are still orbiting around their nucleus. The electrons themselves are spinning, in quotes, not exactly spinning, but doing something kind of like spinning. So they're physically moving. But the electrons are staying in those particular orbits. So what's going to happen is you can take one of these electrons and you can do something called excite it. You can take that electron and you can kick it into a higher orbit. And we'll look at the equation in the next video, but being in a different orbit is going to have a different energy value. And because you have a higher energy value, it is referred to as an excited state. The ground state is the state in which an element is going to want to be in. Everything is at the lowest possible energy. But when it starts absorbing light in terms of photons, it is going to get into excited states. What's going to happen is the electron doesn't actually want to be in this excited state. So it's going to drop back down into the ground state. And when it drops back down, it emits a photon. That energy from going from a high energy to a low energy state has to be conserved. And it's being conserved by generating light. Now, we haven't talked about light in all of its little nitty-gritty details, but light is massless. So we're not generating mass. Light is pure energy. It's a little bit more complicated than that. We have some fields and whatnot we'd have to look into, but just think about it as pure energy, right? We are getting rid of energy, and we're doing so in terms of light instead of things like thermal energy. Now for photoabsorption, let's say we're looking at the same change of state, so from ground state to the first excited state, that same light can come in, it can hit our electron and kick it into the excited state. But for both the emission and the absorption, because we only have specific energy levels for our electron, we can only have specific photons absorbed and emitted. You can also have this done through collision. So let's say you have something that is, we have a bunch of different things we can do. We can use something like an electron beam. So this is just shooting a bunch of electrons into your sample. So if you do that, right, you shoot this electron in, it hits the other electron, gives it energy through conservation of momentum. You're changing the velocity. Therefore, you are changing the kinetic energy value of our electron, putting it in a higher state. And then it too, when it decides I no longer want to be in this excited state, goes down to ground, generates a photon. So again, because Bohr's model states we can only have specific values for our energies, only specific light can be absorbed and emitted. That is what these energy states are telling us. Only certain wavelengths are of importance. So let's talk about some implications of Bohr's model, because Bohr's model is really important for more than just saying electrons had specific values. It made matter stable. If you go back and look at some of the original models of atoms, there's nothing keeping the electrons from colliding in with the nucleus. If that happens, we're going to lose the atomic properties that we need, and matter wouldn't work out the way it does. It also gives us the fact that we can emit and absorb very specific spectrums. These spectrums can also be done by collision, so that gives us a little bit more variety in how we can test materials. Absorption wavelengths are a subset of the wavelengths in emission spectrums. We saw this with the sodium. Not all absorbed wavelengths are emitted wavelengths. Each element of the periodic table has a unique spectrum. So we're not going to go through everything inside of the Bohr model, just because it's kind of this weird, we have to skip so much to get to this point. Like, it's not a, I don't want to, I guess we'd have to gloss over a lot to get to it, but Bohr's actual model tried to explain everything from hydrogen to whatever element they knew at the time. It's, again, not accurate for all of those elements, but based on that general math, it gives us the fact that every element is going to have unique emission and absorption spectrums, which is pretty cool because now we can use that light to help us figure out what element or elements we have. So something we're going to be looking at a little bit more mathematically in the next video is the energy level diagram. So this is just a pictorial representation of the energies for an atom. So here we have just a generic energy diagram. On the left here we have N1 through 5, so these are the energy states, and as we increase number, we are increasing the energy state. So N is equal to 1 is referred to as our ground state. It has a specific energy associated with it. The electron can then go up to N2 through 5 here by absorbing some type of photon, so absorbing some light. And so by absorbing light, it can go to 2, it can go to energy 3, 4, or 5. It can't go anywhere in between. Now what's going to happen is eventually these excited electrons are going to want to go back down to the ground state. The reason there are more emissions than absorptions is I don't have to go back from 4 directly to 1. I can stop at 3, I can go to 2, or I can go to 1. So I'm going to have additional wavelengths because there's only one way up, but there are many ways down. Many different ways in which I can emit a light wave. Only some I can absorb. So this is why, so this E4 to E1, and E1 to E4, same wavelength. E4 to 3 and E4 to 2, different wavelengths. And you can do this for 5 and 3 as well. All right, so that's going to wrap it up for this first video. In the next video, we're going to be looking at a little bit more mathematical representation of what exactly this means.